Octagon.
Hello again. So today we're going to be doing the Law of Cotangents and a very, very similar and equally beautiful relationship with cotangents as I did in the last video with the Law of Tangents. The Law of Tangents, right? This is cotangents. This Law of Cotangents isn't quite as satisfying as the other three. It seems a little odd. It requires a few things sort of to be incorporated, including the inscribed circle of a triangle, which is essentially you get like the in-center of the circle, and in fact I'm actually, before we even get into that, I'm going to show you how that's related to the law of sines, because that has to do with the circumcircle. There's the in-circle and there's the circumcircle, the inscribed circle and circumscribed circle around the triangle. And I'm going to first address that relationship to the law of sines, and then draw the parallel with the in-circle that has to do with the law of cotangents. And then from the law of cotangents we're going to derive the very analogous relationship that the tangent one had in the last video for cotangents. And then in the next video for this little series I'm going to do two proofs of Heron's formula for the area of a triangle, briefly talk about Brahmagupta's formula for the area of a quadrilateral, in that cyclic quadrilateral specifically. And after that, we'll get back to doing the wacky integrals, because I have to do that. I sort of left that one hanging, but I will get to part 2 after I sort of deal with these, because I kind of want to get all of these out of the way. So today we're going to do the law of cotangents. Trusty cup of joe's coming in a frickin' thermos thing today, because I was in my car before drinking this. Still trusty and Joseph. So today we're going to be covering the law of cotangents. Okay, so we're going to be doing the law of cotangents today, and after I prove this statement I will show you a very neat relationship that the cotangent function has to 3 different angles, much like the tangent one did. First I have to sort of introduce a way that you can think of the law of sines, and then relate that to how you can think about the law of cotangents first. We're motivating the conclusion a bit. So I'm going to draw an arbitrary triangle. It could be any triangle. And if you recall from geometry class, high school geometry, which sucks, I know, there is like a bunch of different centers of the triangle. There's the centroid, which is like the geometric physical center of the triangle, which might be somewhere there, which you get by drawing bisectors of one side that come out of the vertex opposite it, and they all intersect in the same point. They are all concurrent at one point, and that is the physical center of the triangle. If you balance the triangle on a pin there, it would stay perfectly balanced. Today we're going to be looking at two of the other different centers. One of them is the in-center, which is the point of intersection of all the angle bisectors of the vertices, and that's for the cotangent one. But first we're going to be looking at perpendicular bisectors. So I need to mark halfway along each side, sort of. Just pretend that's perfectly halfway. And we're just going to draw perpendicular lines that come out of the midpoint of every side. And if I do this properly, then they should all intersect in the same point, right? So those are all perpendicular bisectors. This is not necessarily coming out of the vertex, unless it's an isosceles triangle, which I'm not assuming that it is. But the point is they are all concurrent on that one single point there, and that's because what happens is this perpendicular bisector here is all the points that are the same distance away from these two vertices, right? Because it's the midpoint, it's cutting through the midpoint, and it's sort of staying the same distance. Like if I drew line segments from this point to both of those vertices, they would be the same length, because this is right in the middle. And the same thing goes for this perpendicular bisector and these two vertices, right? They're all the points on a line that are the same distance from these two vertices. And the same thing goes, even though the third one isn't necessary for this, the same thing goes for this third one. All of these points are the same distance from these two vertices. And so what that means is this point is the same distance from all 3 of the vertices, the intersection point, the point of concurrency, is the same distance from all 3 vertices, which means that if we were to connect it to the vertices, and they're all the same distance, that means we can define a circle using these 3 vertices for which that point is the center. And it's called the circumscribed circle, because it goes around the triangle. That was horrendous. Oh my goodness. Hang on a second, let me just make that better. That's not bad. That's not bad. Okay, so that's supposed to be, alright, that's really terrible. I can't deny that. That's supposed to be the center of this circle. I know that it's clearly not. So I'm sorry about that. But essentially what I'm going to do now is I'm going to erase all but a few lines. So we know that we generated that center by putting the perpendicular bisectors of the triangle in place, and so we were able to find the circumcenter, which is the center of the circle that touches every single vertex. Every triangle has one, and because you only need 3 distinct points to determine a circle, every triangle has a unique one. It's their own circumcircle, it's circumscribed circle, so each triangle has their own one. And so because this goes from the center of the circle to one of the vertices, this distance must be the radius of the circle. And so all I'm going to do is continue that to the other side, which means we have a diameter of the circle, correct? And I'm going to just connect these 2 points here. So this vertex, and so these dotted lines are auxiliary lines, the original triangle is still in bold. Okay, I'm going to label these 4 vertices. They're going to be called alpha, beta, gamma, and delta. Okay, so what we're going to do is we're going to relate this to the law of sines now. So what we need is something to do with a right angle. Good thing we have something called the Inscribed angle theorem. I never proved this, but I'm certain you can find a proof of it somewhere on YouTube or on Wikipedia or something like that. And all the Inscribed angle theorem says, and I'll just draw a little diagram of it down here. If you have the center of a circle and an angle subtended, a central angle from there, theta, then if you pick any point between here, around here, like anywhere in this arc, anywhere in this arc, and pick a point on the circle there, and connect it to the same 2 points, then this angle here is always theta over 2. No matter where it is, it could be here, in which case we have this angle here, but this is always half of this central angle. If you connect it to the same 2 points, I'm not going to prove that here, it's a well-established fact, thousands of years old, that we know this to be true. So these angles, any of these angles here, 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 anywhere between these 2 are going to be half of this central angle here, which is going to work in our favor because this is a diameter of the circle, which is the same thing as a central angle of 180 degrees, right? So this is a central angle of 180 degrees, right? And we have a point on the circle which connects to those same 2 points. And because the points on the circle, when connected to the same endpoints of the central angle, have half the angle, then this has to be 90 degrees. Everything here, b plus this other angle that I've added with the auxiliary thing, right? Because this diameter is a central angle of 180 degrees, or pi radians, which means that this inscribed angle has to have half of that measure. So it's 90 degrees or pi over 2 radians, okay? And so because we have that fact, we can start to do trigonometry with this angle here because it's a right triangle. We're going to call this side length c, and this is the diameter of the circle. So this is 2 times the radius of the circle, right? It's 2, we'll call the radius of the circumscribed circle capital R. So the diameter is 2 times capital R. And because we know how to do trigonometry, I'm just going to label it here. So the diameter is 2 times the radius, right? So because we know trigonometry, we know that the sine of delta is c, this side of this original triangle, divided by 2r. So the sine of delta is equal to the side length c divided by 2r, right? But what is the sine of delta? We know that because, what do we know? Oh, yeah. So you can see that with the point alpha and beta from the center, that creates another central angle that's some amount of degrees or radians, I don't know what they are, but you can see that delta and gamma both connect to the same 2 points, right? Gamma goes to alpha and beta, and delta goes to alpha and beta. And because of the inscribed angle theorem, and we know that every angle that's inscribed and connected to the same 2 endpoints are half of the central angle, these are both half of the same number, which means they are the same angle. And because they are the same angle, the sine of delta is equal to the sine of gamma. Correct? Does that make sense, right? Can we see that, right? The angles gamma and delta are both inscribed on the same side of this arc here, of this central angle that connects the center to alpha and beta, so therefore they must both be half of that central angle, and they are half of the same thing, so they must be the same measure. Delta and gamma are the same angle, so their sines are the same. So now that we've done this with delta, we can eliminate this, but look what we have. We have a relationship with sine of gamma and the opposite side to gamma, right? We have c, right? So what we can do is multiply 2r over and divide by the sine of gamma. And look what we end up with. We end up with c divided by the sine of gamma equals 2 times the radius of the circumscribed circle, which gives the circumcenter, right? But because we know that the law of sines is true, this is also equal to b divided by the sine of beta, where b is the side opposite beta. So this is b, right? And this side length is a, right? So b divided by the sine of beta as well as a divided by the sine of alpha. So it's no longer just this weird number that all of these things are equal to, because if you remember in the law of sines video, it turned out that each of these was equal to 2 times the area of the triangle, which we called t, divided by the product of the side lengths, right? We had this weird number, which we didn't really care what it was, just that it equaled all of these things, which means that all 3 of them were equal. That tells us, that means we can relate the radius of the circumscribed circle to the area of the triangle, right? So this, by the way, this was the connection to the law of sines that I wanted to show, that the circumscribed circle has a relationship to the law of sines, which we already proved, so we didn't need to worry about that. Now I'm just going to take a look at these 2 things. So we know that 2 times the radius, or the diameter, of the circumscribed circle is equal to 2 times the area of the triangle divided by the product of the sides. That's what each of those terms in the law of sines was equal to in the law of sines video. Doing a little rearranging, we can see that multiplying, canceling the 2's, we can see that the area of the triangle with side lengths A, B, and C is equal to A times B times C times the radius of the circumscribed circle. And that's kind of funny, right? Like, I mean, isn't that weird? The area of this triangle is equal to the radius of its circumscribed circle times the product of each of its sides. Isn't that strange? If you have a different triangle that has the same circumscribed circle, so just pick any 3 points on the circumference and you have a triangle that has the same circumscribed circle radius, then all you need to know is the length of the sides, and you can find everything you need to know about the area of the circle, which is pretty neat. So that was the connection between the circumscribed circle and the law of sines. So now we're going to see the connection between the inscribed circle and the law of cotangents. I'm going to draw a bigger triangle now, so we can get a real good look at what the inside of it looks like. So the circumscribed circle was found using perpendicular bisectors. This is going to be found using angle bisectors. So we need to not perfectly, but pretty much dead on find the angle bisector of each angle. And because all 3 of these line segments will meet at the same point, I only need to find 2 of them because the center will appear. Because, you know, if 2 of them already intersect in that point, and we know that all 3 will, then I only need 2 of them. So I'm not going to bother bisecting this really, really thin angle. And remember, of course, this is an arbitrary triangle, so this proof will work regardless of what triangle you use. And so, according to my shoddy drawing, this is the center of the inscribed circle. And the inscribed circle is the biggest circle that you can fit inside of a triangle. It is the one that just touches every single side of the triangle, tangent to each side. And that means that the perpendicular distance from this point right to the edge of every side, or right to each side, has to be the radius of that circle. So if I go directly at the circle with these line segments, directly at the triangle with these line segments, you know, perfectly straight at it at right angles, then these will be the radii of the inscribed circle. So theoretically, all 3 of these should be the same length. We'll call this little r, just like we called the radius of the circumscribed circle big R, we're going to call this radius of the inscribed circle little r. So I'm going to do my best now to draw this circle. Don't get mad if it's terrible, because it probably will be. Alright, that wasn't the worst thing I've ever done, but every triangle will have its own inscribed circle, right? The biggest one that you can fit inside the triangle, because it's tangent to every side. So if I moved it down here, it would clearly have to be smaller. If I moved it in towards any corner, it would have to shrink to stay inside the circle. So this is the biggest circle you can draw inside of a triangle. This is how it's related to the law of cotangents. So what we're going to do is we actually need those angle bisectors back. So we're going to call this, we know that the radius of the inscribed circle is little r, and so I'm just going to draw the angle bisectors again, but with dotted lines. We know that all 6 of these little triangles are right triangles because they have these sides that are all little r that go straight at the sides of each of the big triangle, which means they each have right angles in them. So all of these are right triangles. Likewise, they each have a leg of length r. That means that each pair, so this pair of triangles, this pair of triangles, and this pair of triangles are all congruent to each other because of hypotenuse leg congruency, right? We know that they each have the same hypotenuse, like these 2 have the same hypotenuse, these 2 have the same hypotenuse, and these 2 have the same hypotenuse, and they all share a leg of r, which means by hypotenuse leg, we can say that all these 2 triangles are congruent, these are congruent, and these are congruent, correct? Which means that these sides are the same length, these sides are the same length, and these sides are the same length. So these 2 things are the same, these 2 sides are the same, and these 2 sides are the same. We're going to call this angle alpha, we're going to call this side A. We're going to call this angle beta. We're going to call this side B. We're going to call this angle gamma, and we're going to call this side C. Okay, so this is a bit of a cluttered drawing, I know, but keep in mind, we have the three angles, alpha, beta, gamma, the three sides A, B, C, and the three radii of this in circle, which are all the same length, little r. And each of these dotted lines is an angle bisector for alpha, beta, and gamma, which means this angle in here is half of alpha, this angle in here is half of beta, and this angle in here is half of gamma. Okay? The cool thing is that all of them have a side length of r, so we can relate things to do with their angles with r. So before we go on, I need to define one more number, and that's going to be the semi-perimeter. So the semi-perimeter, we'll call it S, and by semi-perimeter I mean half the perimeter of the triangle. So it's going to be the sum of the sides divided by 2. That's it. So it's A plus B plus C divided by 2. Okay, so this is the semi-perimeter. This is S. And it's not too hard to see that we can put each of these little line segments in terms of S and each of the sides. This length right here, and I'm going to write it in a different color now. So from here to here is S minus B. And this right here is S minus C. And we can see that these have to be these because if I add these two together, I should get A. So let's just investigate that real quick. So I'm saying that this is the semi-perimeter minus B, and this is the semi-perimeter minus C. So if I add those two things together, I should get A back because this in total is side length A, right? So let's investigate that. So S minus B plus S minus C equals 2S minus B minus C. But what is 2S? S is the semi-perimeter, so 2S is just the perimeter, right? So 2S is equal to A plus B plus C, and we are subtracting B and C, which means those cancel, and we're just left with A, just like I said we would be. So this is the semi-perimeter minus B, and this is the semi-perimeter minus C. And likewise, analogously, because these are the same, this is also S minus B, and this is also S minus C. And of course, I think it's pretty easy to deduce that these two will be S minus A. So S is not some other weird variable, it's just the sum of all the sides divided by 2. And so now that we've gotten all of that crap out of the way, we can finally find the law of cotangents. So remember, all of these dotted lines are angle bisectors to each of the three angles of the triangle, which means this is alpha divided by 2, this is beta divided by 2, and this is gamma divided by 2. Okay, so those are the angles that I'm going to be considering. And we're going to take the cotangent of all of those angles. Okay? So let's start with alpha. The cotangent of alpha over 2, remember what's cotangent? It's the reciprocal of tangent. Tangent is opposite over adjacent, so cotangent must be adjacent over opposite. And with regard, because this is the dotted line is the hypotenuse, then the adjacent side to alpha over 2 is S minus A, and the opposite side is little r. So we know that the cotangent of alpha over 2 is equal to S minus A over little r. We also know that the cotangent of beta over 2 is S minus B over little r. And we also know that the did I say cosine of beta over 2? I meant cotangent of beta over 2 if I did. And the cotangent of gamma over 2 equals S minus C over r. This is how we're going to deduce the law of cosines. Because, I'm sorry, I keep saying cosine, the law of cotangent. But if this was not entirely clear, just draw this out yourself. You'll see all the relationships. The dotted lines are angle bisectors of each of these vertices. These lines here that come out from the incenter to the sides are each radii of this circle. And this circle is the circle, the inscribed circle of the triangle. And S is, of course, the semi-perimeter. It's half of the entire distance around the triangle. I'm going to erase the triangle now, and we're going to look just at these formulas that we've derived. Okay, so we have these three relationships now, and remember S is the semi-perimeter, A plus B plus C over 2. Look at this, we have a common factor of little r in all of these. So I'm going to divide both sides by S minus A, S minus B, and S minus C, etc. So we're going to divide this side by S minus A. We're going to divide both sides by S minus B, get out of here green, and we're going to divide both sides by S minus C. And would you look at that, we have 1, 2, 3 ways of writing 1 divided by the radius of the incircle in terms of the cotangent of each of the 3 angles divided by the semiperimeter minus the opposite side of that angle. This is the law of cotangents. So this is the fact, big fat QED. I know I didn't say it out from the beginning that this is what we were going to do, but I didn't feel like explaining what S was at the beginning of the video. So this is the radius of the inscribed circle, the tiny little circle. It's absolutely lovely. I mean, look at that. It's just beautiful. So now that I've shown you the law of cotangents, I'm going to show you a similar fact that we did with the tangent function. So we're going to say that, assume again, like we did with the tangents, that alpha plus beta plus gamma, not pi this time, we're going to do pi over 2. So these 3 angles do not add up to 180 degrees, they add up to 90 degrees. And so we need to consider the cotangent of alpha plus the cotangent of beta plus the cotangent of gamma. But remember, cotangent and tangent are complementary functions, right? They're not just reciprocals of each other, they're also complementary, which means if I apply tangent to the complementary versions of these angles, I'll get the same number, right? And the complementary version is just pi over 2 minus each of these things. This is going to be equal to the tangent of pi over 2 minus alpha plus the tangent of pi over 2 minus beta plus the tangent of pi over 2 minus gamma. What is this plus this plus this? Well, let's see. So we're considering the 3 angles that we have inside the tangent function now. Pi over 2 minus alpha, pi over 2 minus beta, and pi over 2 minus gamma. So pi over 2 minus alpha plus pi over 2 minus beta plus pi over 2 minus gamma. We have pi over 2 plus pi over 2 plus pi over 2, which equals 3 pi over 2. And we have alpha, negative alpha minus beta minus gamma, which is just negative pi over 2. Right? So this is equal to 3 pi over 2 minus pi over 2, and how much does that equal to? That's equal to pi. And that's important because that means that this angle plus this angle plus this angle equals pi, which means the weird relationship that I demonstrated for tangents in the last video applies to these 3 angles. So this is equal to the tangent of pi over 2 minus alpha times the tangent of pi over 2 minus beta times the tangent of pi over 2 minus gamma. But and that's just from the last video using the tangent thing I showed, right? Because these 3 angles add up to pi, which means the tangent rule applies. But because each of these was equal to the cotangents from before, I can rewrite all 3 of these as these 3 cotangents. So we have that this is equal to the cotangent of alpha times the cotangent of beta times the cotangent of gamma. This is the statement I wanted to prove. That the cotangent of alpha plus the cotangent of beta plus the cotangent of gamma is equal to the cotangent of alpha times the cotangent of beta times the cotangent of gamma if alpha plus beta plus gamma equals pi over 2. So the one with tangents is true. This one right here that we used to prove this cotangent one, this is true when the angles add up to pi. And this one for cotangents is true when the angles add up to pi over 2. But they're both the same looking relationship with slightly different functions, and it's just absolutely beautiful. So thank you for watching the proof of the law of cotangents, and this was the similar relationship for the cotangents as we did in the tangent in the last video. And now that we've got all 4 of these laws for sines, cosines, tangents, and cotangents, we're going to finally prove in 2 different ways in the next video how to arrive at Heron's formula for the area of triangles. Thank you very much for watching.